Chapter 7. So I've decided to go over the first example. So we are going to prove the addition formulae, which is sine alpha plus beta equals sine alpha cos beta plus cos alpha sine beta. You will need to memorize these. It will be easier for you, although they do appear in the formula booklet. If you notice, sine alpha starts with sine alpha and then you followed by cos beta, so you need to have both angles, and then the roles are reversed. For cos alpha plus beta, remember cos is contrary, however it still starts with cos. It's cos alpha, but then it's followed by cos beta, and it's just different. Minus, because there's a plus, like I said, contrary, and sine alpha, sine beta. So we are going to prove those two results. One proof I've already shown you in the previous video. This proof is the same proof that appears in example 1 in your textbook. So we're going to do the proof by following this diagram. So again, geometrical reference here, that's what we are going to rely on. So the first thing we're going to realize that in this shape over here, you've got a triangle ACE, and the length AE is of unit 1. So I withdrawn it over here. You've got AE is equal to 1. And then in this triangle, you can actually find the sides EC and AC by using simple trigonometry. So this angle here, we are going to name that as angle beta. So if you can see in this with the simple trigonometry, EC over 1, so opposite over hypotenuse, is equal to sine beta. So EC is equal to sine beta. So I'm going to pop that sine beta over here. And then doing the same, AC over 1 is equal to cos beta. So AC is equal to cos beta. So then I've extracted the triangle ABC over here. Now, having found cos beta as the hypotenuse of length AC, hypotenuse of our triangle, we can again do simple trigonometry to find the length BC and AB in terms of cos beta, which is the hypotenuse, and either sine or cos alpha. So CB, which is opposite over hypotenuse, which is cos B, that will give you sine alpha. So you could see that CB is equal to sine alpha cos beta. So let me write it down. CB is sine alpha cos beta. And then AB, which is adjacent, divided by hypotenuse, which is cos B, this is going to be equal to cos alpha. So AB must be equal to cos alpha cos beta. So let's put it down. All of that is cos alpha cos beta. Now there's another right angle triangle. It's ADE, but before, there's one more that I forgot to draw. Let's extract this triangle EFC or CEF. Let's draw it there. So it's CEF. Because in this triangle, let's actually think, do we know any of the angles inside this triangle? Well, if you look very carefully, you've got those two triangles. You can see that they are similar triangles. This angle is equal to that. And then alpha is over here. Okay, so we've established that this angle over here is alternate angle to alpha. Or you can use the rule that it's a right angle triangle and angles add up to 180 degrees. these two are opposite angles, vertically opposite angles, which are equal. Anyway, so you've got alpha over here. So this way you can find that this angle, therefore, is going to be 90 minus alpha, because this angle here, which is ACE, is a right angle. If that's 90 minus alpha, again, this angle at point F, so it's CFE, that's 90 degrees. Therefore, angle here must be alpha. These two in a right angle triangle add up to 90. So if that's 90 minus alpha, this one is alpha. So let me put alpha over here. There you go. So in this triangle, you've got the side here, that's sine beta, that we found that previously. This is hypotenuse. So FC over, which is opposite, over sine beta must be equal to sine alpha. So FC is sine alpha, sine beta. So this is that side here. So it's sine alpha, sine beta. There you go. And let's find FE. I'll do this one quicker. This is simply going to be cos alpha sine beta. You can do it slowly as well if you wish to. So this is cos alpha sine beta. Now, having done this, we can now have a quick look at working out our results. So have a look at let's look at this last triangle over here. This angle here is alpha plus beta, so this is alpha plus beta. There you go. This is a triangle with a hypotenuse equal to 1, so I will do this one quicker. So side AD is going to be AD over 1 is equal to cos alpha plus beta. So this one will be cos alpha plus beta. And side ED will be sine alpha plus beta. There you go. So this one here is cos alpha plus beta. So that's this length. And this length over here, let me just put it, okay, did not allow enough room for there. So this is why we've got AG here. This is going to be sine alpha plus beta. Now we are ready to do the results. So that side that I've just written down, sine alpha plus beta, which is our side AG, this must be equal to, look very carefully, BC add EF. And BC is sine alpha cos beta, and EF is cos alpha sine beta. Easy. Okay, and then let's look at that side over here. So this one, which is side AD, this must be equal to our side AB, which is all the way here across, subtract that side here, DB, which is the same as FC. There you go. So these two must add up to our AB, so minus FC. So this one must be equal to, so that one will give us, let me just write it here, cos alpha plus beta is equal to AB, which is cos alpha cos beta subtract sine alpha sine beta, which are our two top results. Okay, sine alpha sine beta. On top of this, there are a few more results that you need to learn. Okay, so jot them down really quickly. We are going to prove the next, well, at least two of them, and you should be able to prove the others by following the example. So of course you can have, we had sine A plus B. You can also have sine A minus B. Sine A minus B is simply the same as sine A plus B, but there is a minus in the middle. So it's sine A cos B minus cos A sine B. You can also have cos A minus B. This time it's the same as before, but there is a plus. So it's cos A cos B plus sine A sine B. Perfect. And then you can also have tan A plus B. That's going to be tan A. It's a fraction. On the top you put tan A. All of them start with, if you start writing sine A here, you start with sine A, cos A, tan A. So there is a plus on the top, tan A plus tan B. And there you've got 1 minus tan A multiplied by tan B. Now, in the formula booklet, the result for A minus B is actually included within the result for the addition formula. All you need to do now is swap these to opposite signs. So when there is a plus, it becomes minus. When there was a minus, that would be plus. Okay, so we're going to move on to example 2. And in the example 2, we are going to prove, using the results from before, we shall prove the two results, the two results that I've written, cos A minus B and tan A plus B. So how can I use the result for cos A plus B? Well, cos A plus B, I will use alpha, it would be easier for this one. Alpha plus beta. We've proven that cos alpha plus beta is cos alpha times cos beta minus sine alpha sine beta. There you go. To now, generate the result for minus beta, we are going to replace our beta, so alpha with A and beta with minus B. There you go. So we are going to get cos alpha plus minus, or rather A, sorry, we're replacing it, minus B. And you are going to get cos A, cos minus B, minus sine A, sine minus B. Now, cos is an even function. So when you draw a cos graph, imagine there's my minus B, and there is my cos graph. So it doesn't matter where it is, somewhere it's a negative angle. So it's going to be exactly the same as cos B. So its property of being even function, which means that it's symmetrical about the y-axis. So whatever the negative angles get, the positive angles get as well. So you are going to get cos A and cos B. Now over here, we are going to have to look at sine B. So if you remember how to draw sine, do the same thing. Now, it's not an even function. Sine happens to be an odd function. There you go. So that means if I want to find the expression for sine minus B, I'm going to get minus sine B. So in size, they are exactly the same, but they are in opposite value, or opposite signs. So yeah, so in size they are the same, but in opposite value. So minus that will give you sine minus beta. So this can be replaced with minus sine B. So effectively you're going to get cos A, cos B, and then you get minus times minus become a plus. So it's sine A, sine B. So this is our result proven. Okay, and it's in the formula booklet. Now Okay, for proving tan A plus B, we are going to rewrite tan A plus B as sine A plus B over cos A plus B. Now, we can now express the numerator as our expansion. So sine A cos B plus cos A sine B. And in the denominator, we are going to have cos A cos B minus sine A sine B. Now this result we've already quoted before, and we're going to, if you look at this, if you know what you are aiming for, tan A plus tan B on the top, and then you've got 1 minus tan A tan B. Because what it is, it's expressed in terms of tans, so you're looking for the identity that involves tan A, separate tan A's and tan B's. At the moment, I've got sine A's and sine B's, so I need to create those tans. So the way to think about it is you want to create fractions within fractions, and those fractions that you are going to then convert to tan A's and tan B's will have causes in the denominator. So I need to divide by cos A and by cos B. Another way of thinking about it, because I aim to get 1 as the first term in the denominator, you kind of think about changing this to 1. You can only do it by dividing by cos A and cos B. So that's what we are going to do. Cos A cos B is going to be our dividing factor of the numerator and the denominator. So whatever you do to the top, you must do to the bottom. So I need to get ready for a double-decker expression. So it's sine A, and you really, in the proof, you need to write it down. There's no shortcuts. Cos A, cos B, plus here I've got cos A sine B over cos A cos B, and then you've got cos A cos B divided by cos A cos B minus sine A and sine B divided by cos A and cos B. So now I'm going to do the cancelling down. So I like to do it in a different color and just be clear. So here you've got a fraction. You can see that this will become tan A, and that cancels. I like to put 1 and 1 there. This one here cancels, 1 and 1, and this one will become tan B, and we wanted tan A plus tan B. Over here, cos A and cos A and cos B and cos B, they will cancel and be 1 over 1, which is 1, and there's nothing that cancels over here. So you've got sine A over cos A, that will become tan A and tan B. So you've got tan A plus tan B divided by 1 minus the product of tan A and tan B. So it's proven if it's a proof. Okay, let's move on to example 3. So in this example, we are going to just check whether we've got exercise coming up after this example. After example 4. Okay, so in this example, we are asked to prove that cos A over sine B minus sine A over cos B is equal to cos A plus B over sine B cos B. In any proof, it's start with the side that you can do something to. So normally it's something that you can expand or something that looks a bit more busy. So here you've got a choice actually. You can either add these two together, or you can expand the right hand side and then try and get it to that form. So I'm going to actually start from the right hand side. Sometimes, and it's not sometimes, but very often, it's a good idea to do a little bit of work to both sides and show that they meet in the middle. Okay, so it's cos A, so rewrite that right hand side, and then sine B, and then cos B on the bottom. Okay, so normally you put equal sign underneath the equal sign in the proof. So we are going to expand the numerator using addition formula. So we've got cos A, cos B, subtract sine A, sine B. And then the denominator is the same. Okay, so here we've got to separate these into two terms. So it's cos A, cos B, divided by sine B, cos B. So it's over, it's a fraction, minus. You've got sine A, sine B, over sine B, cos B. So I'll continue my proof over here. Over here again, let's use the pen. You've got this here. We want to cos A, yeah, that's perfect. This one will cancel. And then you've got sine A, sine B. Sine B cancels. And then you've got sine A over cos B that's left over, which is our left-hand side. So let's write it down. Cos A over sine B minus sine A over cos B, which is our left-hand side. So it's proven or shown. Okay, let's look at the next one. So it's similar idea to a proof, but this time we are asked to express tan x in terms of tan y and not having any tans at all. Well, that's not a problem. What's the first thing that crops into my mind is to do the expansions, because tan x, I want to end up with tan x, and then on the right hand side I'll have expression involving tan y, but tan x is sine x over cos x, and tan y can be expressed as sine y over cos y. So I'm hoping to create these from the expression that I obtain after expanding both sides. So let's expand these. So it's 2 sine x cos y plus cos x sine y equals 3 cos x cos y. This one will go to a plus sine x sine y. So let's expand, multiply by 2, and then think what can we do to create those fractions that can be converted into tan x and tan y. So almost done. Okay, so I want to have fractions with causes in the bottom, so that tells me that I need to divide by cos x and cos y. If I divide every term by cos x and cos y, provided neither cos nor x nor cos y is ever equal to 0, I'll have identity that works. So 2 sine x cos y needs to be divided by cos x cos y. Add 2 cos x sine y need to be divided by cos x cos y. Here we've got 3 cos x cos y needs to be divided by cos x cos y, plus, I'll squeeze that, sine x sine y divided by cos x cos y. Again, let's use my red pen to gather the terms. So here you've got sine x over cos x, that will create a tan, this will cancel. Here we've got, this will create tan y, this will cancel, and then these both will disappear. And here we are going to have 1 tan x and another tan y, so 3 tan x tan y. So let's write it in terms of tan. 2 tan x plus, here we've got 2 tan y equals to 3 times 1, so it's 3 plus 3 tan x tan y. Because we want to have tan x in terms of tan y, that means your tan x needs to be made the subject of this expression. So anything with tan x need to be shifted onto one side. So you've got 2 lots of tan x, and then you've got 3 tan y, lots of tan x here. And on the other side you will have 3, and then minus 2 tan y. There you go. So you've got tan x can be pulled outside the bracket. So you've got 2 minus 3 tan y lots is equal to 3 minus 2 tan y. The last thing is divide how many tan x's we've got. 3, which will go into the denominator. So that is 2 minus 3 tan y. So this is tan x expressed in terms of tan y. So now you're ready to go ahead and have a go at exercise 7a.